Okay, let's unpack this. In the fast-paced world of artificial intelligence and machine learning, we're relentlessly pushing the boundaries of what's possible, right?
Yeah, constantly. Feels like every week there's something new.
Exactly. And every new breakthrough demands more computing power, more speed, and critically, far greater energy efficiency. That last one seems huge now.
Oh, absolutely critical.
Hmm.
For decades, digital computing has been the undisputed champion, the king of the hill, really, dominating pretty much everything.
Totally. But lurking in the shadows, maybe, there's always been this tantalizing, almost mythical promise of analog computing.
You've hit the nail on the head there.
Yeah.
Analog computing has truly always held immense, almost irresistible potential for machine learning.
Why is that exactly? What's the core appeal?
Well, primarily because of its inherent ability to offer significantly higher computational density, so like
Mm.
more calculations in a smaller space, and far greater energy efficiency compared to its digital counterparts.
Okay, density and efficiency. That sounds good.
Think of it like this. Digital computing works by converting everything into discrete bits, ones and zeros, like flipping light switches on and off, right?
Right, binary.
Analog, on the other hand, performs calculations directly with continuous signals, more like adjusting a dimmer switch. It's often a more natural way to process real-world data, which is inherently continuous.
Makes sense.
And here's where it gets really fascinating. For ML machine learning models, especially during their training phase, they seem to possess this unique superpower. They can actually learn to compensate for some of analog's traditional Achilles heels.
What kind of heels are we talking about?
Things like slight device imperfections, where two transistors aren't quite identical, or nonlinearity in the response. Analog artifacts, basically.
Ah, okay. Stuff that would normally break a precise calculation.
Exactly. But ML's adaptive nature is, in many ways, a perfect fit for analog's unique, sometimes quirky characteristics. It can learn around the imperfections.
That sounds absolutely incredible. So if analog offers such profound advantages, more power, less energy, and ML can even forgive its imperfections, then why isn't it powering every AI system we use today?
Yeah, that's the million-dollar question, isn't it?
What's the catch? Why haven't we seen it truly scale up for the incredibly complex AI tasks that are driving innovation, especially when we talk about, the bleeding edge of chip manufacturing?
Is precisely the core challenge this deep dive is designed to address.
Yeah.
The catch has historically been a monumental hurdle, the sheer lack of scalability in traditional analog circuits.
Scalability, okay.
Unlike digital designs, where a piece of circuitry can be pretty easily copied and pasted or mapped across different manufacturing process nodes, imagine moving a design from an older, say, 180 nanometer technology to a cutting-edge, incredibly precise 7 nanometer one.
Which happens all the time in digital.
Right. Analog circuits just haven't had that luxury. This fundamental difficulty stems from critical differences in how transistors behave under various biasing conditions, how they respond to temperature fluctuations, and their inherently limited dynamic range.
So it's not just about shrinking things down.
Not at all. It means that if you design a conventional analog circuit for one specific technology, one specific process node, it often won't work optimally, or sometimes even at all, in another, without an incredibly costly and time-consuming complete redesign from the ground up.
Wow. So it's been like a bespoke tailoring job every single time.
Pretty much, yeah. Rather than a mass-produced standard solution like you get with digital standard cells,
Yeah.
it's been a major bottleneck.
So if that's the brick wall analog has repeatedly hit, our mission today is to dive deep into a paper that claims to have found a sledgehammer.
That's a good way to put it.
We're exploring a truly groundbreaking piece of research titled Process, Bias, and Temperature Scalable CMOS Analog Computing Circuits for Machine Learning by Pratik Kumar and his brilliant colleagues.
A really significant piece of work.
And this work introduces a novel and incredibly clever approach called shape-based analog computing, or SAC, the promise, to make analog circuits as scalable and robust as their digital siblings, specifically tailored for the demanding world of machine learning.
That's the core idea. Scalability and robustness for analog ML.
Get ready for some serious aha moments, because this really could change how we think about AI hardware.
Let's pick up on that promise a bit more. You touched on the allure of analog for ML. Can we elaborate on why researchers are so incredibly keen on this pairing? What makes machine learning such a compelling partner for analog's unique characteristics, beyond just the raw efficiency?
Sure. Well, beyond the sheer computational density and energy efficiency we initially discussed, machine learning training processes offer this unique, almost symbiotic advantage. They allow for both offline and online calibration.
Calibration. Okay, what does that mean in practice? What this means is that the system can actively learn to compensate for those inherent analog imperfections. I mentioned things like device mismatch, where, two supposedly identical transistors aren't quite identical after manufacturing.
Right, the real-world variation.
Exactly. Or nonlinearity, where a circuit's response isn't perfectly proportional to its input. In traditional analog design, these imperfections are often catastrophic. Even a tiny variation in a resistor value might completely throw off a calculation.
Yeah, I can see how that would be a nightmare.
But with ML, the learning algorithm can effectively tune around or train past these imperfections during its training phase. It learns with the imperfections, making the entire system incredibly resilient and robust.
So it's like the ML algorithm acts as a clever interpreter, understanding the unique dialect of the analog hardware, even with its little stutters and accents.
That's a perfect analogy. It transforms what was once considered a bug, a major flaw, in analog design into something manageable, almost a feature, because the system adapts to the specific hardware it's running on.
Okay, that makes a lot of sense.
And we've seen examples of earlier analog ML implementations that showed great promise for specific, often simpler tasks. But those systems often hit a wall when it came to flexibility and, crucially, reusability or scalability.
How so?
They were typically custom-built, carefully hand-tuned for one specific task or one specific chip generation. If you wanted to update the underlying technology, maybe move to a smaller node, or even just modify the task slightly, it was often back to the drawing board.
Like redesigning an entire engine for every single car model.
Exactly. Very time-consuming, very expensive, not scalable.
So ML can be remarkably forgiving of analog's quirks, which is a huge step forward. But as you mentioned, then comes that thorny, persistent issue of scaling. This is where digital computing has truly been king, isn't it? It's been its undeniable superpower.
Oh, absolutely, no question. Digital's crowning achievement, and the primary reason for its nearly universal dominance, is its unparalleled process scalability.
Can you break that down a bit?
Sure, imagine a digital circuit module.
Yeah.
Let's say a basic logic gate, like an AND gate, or maybe a small block for adding numbers. Once you design that block, its logic function, it can be mapped from an older, larger feature-size process node. Think of something like an established 180 nanometer technology.
Okay, like older tech.
Right. And you can map that same logical design to a much more advanced, smaller, and denser one, like a cutting-edge 7-nanometer FinFET process with minimal or often no circuit modification needed at the functional level.
The logic stays the same, it just gets smaller and faster.
Precisely. The underlying logical function remains exactly the same. The physical implementation simply shrinks down, becoming faster, consuming less power, and allowing for significantly higher compute density on the chip. This incredible consistency in design methodology is a huge enabler for rapid innovation.
Yeah, it lets chip designers just take advantage of new manufacturing without reinventing the wheel every time.
Exactly. It's why our phones get more powerful every year without, suddenly becoming suitcase-sized.
Right. Okay, here's where it gets really interesting. You've explained why digital scales so beautifully. But for analog, it's been a completely different story. Why is it so incredibly difficult to scale analog computing circuits across these dramatically different process nodes? Why can't we simply take an analog circuit and shrink it, expecting it to work just as well, if not better, like we do with digital?
It all boils down to the fundamental physics and behavior of the transistors themselves, which change quite dramatically as you scale down. It's not just about size.
How do they change?
Well, think of a transistor as having different gears or operating modes for how it conducts current. There's a weak inversion gear, which is great for ultra-low power but might be slower. Then there's strong inversion, which is fast but uses more power. And in between, there's moderate inversion, offering a kind of balance.
Okay, different operating modes.
Historically, many conventional analog circuits were specifically designed to work optimally in one of these specific gears or operating regimes. They relied on the transistor behaving in a very particular way in that regime.
Right. Fine-tuned for one mode.
Exactly. Now, when you shrink a transistor from, say, 180 millimeters down to 7 millimeter, the optimal gear often shifts. The characteristics change. For instance, if you look at the paper's Figure 1, which compares transistor performance using a figure of merit, basically how efficient and fast a transistor is for a given power, you see that in a 7-nanometer FinFET process, the best performance and widest dynamic range are often achieved in the moderate inversion regime.
Which is different from where older designs might have focused.
Precisely. Many older analog designs relied heavily on weak or strong inversion for specific benefits. So the very physics of how current flows in response to voltage is altered. The relationships change.
Oh, okay.
Not only that, but the maximum supply voltages also plummet. They go from around 1.8 volts for 180 millimeters down to a mere zero point 0.7 volts for 7 millimeter.
Wow, that's a huge drop.
It is, and this shrinking voltage headroom severely impacts the signal range of precision you can achieve in analog circuits. Less voltage means less room for your signal before you hit the noise floor or the power rail.
So trying to directly scale an old analog design to a new process node is problematic.
Extremely problematic. It's like trying to use a classic car engine, designed for specific fuel and conditions. In a modern electric vehicle, the underlying principles are just too different for a simple transfer. It's why analog design has largely remained a bit of a black art, requiring highly specialized expertise for each new technology generation.
A black art that doesn't scale easily. Got it. So we've identified this huge chasm, analog's immense potential for AI, constantly undermined by its historical inability to scale predictably. So what does this all mean? How do the researchers in this paper actually propose to bridge this fundamental gap? How do they plan to bring analog into the scalable, predictable future that digital has enjoyed for so long?
Well, the authors propose a really novel approach, and it's built upon a generalization of a framework they previously reported called margin propagation. But at its very core, it's all about a concept they call the multi-spline approach.
Multi-spline approach. Okay, what does that mean? Can you visualize it for us?
Yeah, absolutely. Imagine you're trying to draw a very complex, curvy line, let's say an exponential function, which is a common shape needed in many AI calculations.
Okay, like e to the x.
Exactly. Traditionally, an analog circuit might try to approximate that curve with one long straight line segment. It's a rough fit, right? And the further you go along the curve, the less accurate that single line becomes.
Yeah, it drifts away from the real curve.
Precisely. But what if, instead of one long line, you use multiple shorter line segments or splines, each perfectly tuned to a different smaller part of that overall curve? Each spline can follow its specific segment with much higher precision.
I get it. It's like using a series of small, precise steps to trace a complex path, rather than one big, less accurate jump. That immediately sounds more adaptable and much more precise.
Exactly. That's the core intuition. As beautifully illustrated in Figure 2a from the paper, using multiple splines, where S represents the number of splines and S is greater than 1, provides a significantly better and more accurate approximation of that target nonlinear function.
Like the log sum exp you mentioned.
Yes, they use log sum exp as a key example, which is a powerful and computationally intensive building block in many machine learning algorithms. But crucially, this multi-spline approach isn't just about accuracy. It gives designers a direct and explicit knob to twist.
A knob?
Yeah, a control,
Control.
a trade-off between computational accuracy, speed, and power consumption. You can decide how many splines you need based on the specific demands of your application. More splines mean more accuracy, but maybe a bit more power or area. Fewer splines mean less accuracy, but potentially faster and lower power.
Okay, so it gives the designer control over that trade-off.
Exactly. And this generalized framework, which allows for these adaptable shapes of computation, is what they've aptly named shape-based analog computing, or SAC.
Shape-based. I like that. And you mentioned flexibility in the functions.
Right. What's particularly innovative is the flexibility of the actual mathematical functions, the G functions, within SAC. As long as these functions meet certain fundamental mathematical properties, they must always be positive, continuously increasing, monotonic, and start at 0 when the input is 0. They can be physically implemented using transistors.
So it doesn't have to be exactly an exponential, just something with those basic properties.
Exactly. This freedom to choose the underlying mathematical shape that the physical transistor will realize is why they call it shape-based computing. It liberates designers from the constraints of trying to perfectly mimic rigid, fixed mathematical forms, offering a tremendous amount of design freedom and versatility.
So if I'm understanding this correctly, the ultimate goal here is to give analog circuits the same kind of design flexibility and, more importantly, the scalability that digital circuits have always enjoyed. How does SAC actually achieve this digital-like quality? How can you design a function once and then port it to a brand new chip manufacturing technology without having to redesign everything from scratch?
The multi-spline approach is truly the linchpin here. It provides designers with that unprecedented control over the trade-offs we just discussed. Accuracy versus speed versus power.
Right, the tuning knob.
By simply adjusting the number of splines, S, You can dial in your desired balance. This is a fundamental design lever, a tuning knob that digital engineers are very familiar with, but which has been largely absent or very implicit in traditional analog design.
So it makes analog design feel more like digital design.
In a way, yes, if your AI model needs higher precision for a critical task, you add more splines. If you can tolerate a bit less precision for much lower power or higher speed, you use fewer. This flexibility is a paradigm shift.
Okay, that's the flexibility part. What about the robustness and porting across technologies?
Right. So SAC circuits are not just designed for precision, they are engineered from the ground up for remarkable robustness. They are designed to maintain their performance characteristics across those widely varying biasing regimes, weak, moderate, and strong inversion.
The gears we talked about.
Exactly. And across vastly different process nodes, from that older 180 mm planar CMOS all the way down to a bleeding edge 7 mm FinFET. And perhaps most impressively, they hold up across a wide range of operating temperatures, from freezing -45 Celsius to scorching 125 Celsius.
That's huge. Temperature is usually a killer for analog.
It really is.
Yeah.
So the implication here is profound. SAC circuits can truly be treated as synthesizable analog standard cells.
Synthesizable analog standard cells. That sounds
It
revolutionary.
really is. This means you can design a complex analog function once, capture its behavior, and then theoretically port it across different generations of chip technologies with the same ease and predictability you'd expect from a digital logic gate in a standard library.
That is a colossal shift. It truly opens the door for automated design tools for analog, something that has been the holy grail for circuit designers for decades. Imagine the reduction in manual effort.
Exactly. And the specialized expertise currently required for custom analog design. This makes analog AI potentially much more accessible and faster to develop.
This all sounds very sophisticated in theory, talking about multi-splines and mathematical functions in these generalized frameworks. But let's get down to the brass tacks. How do these brilliant researchers actually build these shape-based functions using real-world transistors?
Yeah.
You know, the actual silicon and metal of circuit design. What's the engineering magic under the hood?
Okay, yeah, let's look under the hood. It actually comes down to elegantly harnessing the fundamental physics of MOSFETs, the metal oxide semiconductor field effect transistors, which, frankly, are the unsung heroes and workhorses of virtually all modern electronics.
The basic building block.
The basic building block. The drain-to-source current, which is simply the flow of electricity through a MOSFET, can be expressed mathematically as a difference between what they call forward and reverse currents that depend on the gate and source voltages. The crucial insight here, the real clever part, is that this current flow function, which describes the transistor's natural electrical behavior, inherently satisfies those specific mathematical properties required for the SAC framework. Remember, always positive, monotonic, starting at 0.
So the transistor naturally behaves in a way that fits the SAC model.
Exactly. It's like finding that the natural curve of a specific tree branch perfectly matches the curve you need for a complex archway. The physics is doing the heavy lifting for you.
Yeah.
And this remarkable consistency holds true regardless of the specific transistor model you use, like EKV or ACM, different ways of modeling transistors, or its operating gear, weak, moderate, strong inversion, or even the underlying chip technology, be it a traditional MOSFET or an advanced FinFET.
Wow, so they found a way to use the inherent physics instead of fighting against it?
Precisely. And the paper then shows incredibly practical CMOS circuit implementations. If you were looking at the schematics, Figure 2b would show you the N-type version using an NOS transistor, and Figure 2c, the P-type version using a PMOS transistor.
And are these circuits complex?
Surprisingly simple, actually. Each basic SAC unit uses just a single MOSFET and a diode. That's it. The input to the circuit is represented as a current, X(Ij), and the output, the calculated function Hx, is also a current.
Current in, current out. Okay.
And they cleverly use Kirchhoff's current law, or KCL, a fundamental rule of circuit analysis that basically says current doesn't just disappear at a junction.
Right, what goes in must come out.
Exactly. You use KCL at a specific node labeled VB in the diagrams to satisfy the underlying nonlinear mathematical constraint, equation 11 in the paper. The true beauty lies in this simplicity. These incredibly straightforward building blocks, when combined using the SAC framework, like connecting multiple splines, can create those desired complex computational shapes that machine learning needs.
So they're essentially taking the natural, inherent electrical behavior of a transistor, how it naturally responds to voltage and current, and cleverly molding that natural response into these scalable, programmable, computational shapes. It's almost like they've discovered the hidden computational power already embedded within the physics of the transistor itself.
That's a great way to put it. And while that theoretical elegance is compelling, robust performance in the chaotic face of real-world manufacturing variations,
Mm.
fluctuating operating conditions, and temperature swings is paramount for any practical application. You need it to actually work reliably.
Absolutely. Theory is one thing.
Right. So the researchers provide extensive evidence from simulations to definitively prove this robustness. This is where they really back up the claims.
Okay, let's see the proof. What did the simulations show?
Let's break down these critical simulations. First, process scalability. If you look at Figure 3A and 3B in the paper, they visually demonstrate that the basic SAC shape function, the HX we've been talking about, remains remarkably consistent. And this consistency holds whether it's implemented in an older, more established 180mm planar CMOF process or a state-of-the-art 7mm FinFET process.
So the same shape works on old tech and new tech.
Pretty much, yeah. They show this for both a single spline, S1, which gives more general approximation, and for 4 splines, S4, which, as expected, improve accuracy. But the critical takeaway here is that the fundamental shape and, more importantly, its scalability are maintained across drastically different and traditionally incompatible chip technologies.
That's the key maintained across technologies, meaning less redesign work.
Exactly. That's a huge time and cost saver for designers. Then consider bias scalability. Figures 3C for 180 planar and third for 7mm visibly demonstrate that the SAC shape remains robust across all 3 major transistor operating gears or biasing regimes: weak inversion, WI, moderate inversion, MI, and strong inversion, SI.
So it works well no matter which gear the transistor happens to be in.
Within reason, yes. This is incredibly vital because these regimes offer different trade-offs in terms of speed, power, and linearity. The fact that SAC can operate effectively in any of them and that its characteristic shape is preserved within a well-defined margin determined by design parameters means it's astonishingly flexible and far less sensitive to the exact biasing condition.
Which can fluctuate in real circuits, right?
Exactly, due to manufacturing variations or environmental factors like temperature changes. Speaking of which.
Temperature, the big one for analog.
Right. Now, perhaps one of the most fantastic and immediately impactful results relates to temperature scalability.
Yeah.
Figure 4A clearly illustrates that the SAC shape function is almost immune to changes in temperature. It shows consistent behavior across an enormous range, from a truly freezing mode at 45 degrees Celsius all the way up to a scorching 125 degrees Celsius.
Wow, almost immune. That's incredible.
It really is. This eliminates a huge variable that traditionally plagues analog circuit design. Temperature drift is a notorious headache for analog engineers, often requiring complex, power-hungry compensation circuits just to keep things stable.
So SAC might not need those?
Potentially much simpler compensation, or maybe none at all for some applications. SAC's inherent robustness to temperature is, frankly, a massive advantage. It simplifies design and improves reliability dramatically.
Okay, so process, bias, temperature, any other robustness checks?
Yes. Beyond these big 3, the paper also confirms other robustness factors. The basic SAC circuit maintains its shape despite device mismatch, those slight variations in identical transistors due to manufacturing imperfections, up to a significant 5%, as seen in Figure 4B.
Which is a realistic level of variation.
It is. And it also holds up admirably against variations in power supply voltage, another common issue in complex systems where the voltage might dip or fluctuate slightly. So these results collectively solidify SAC's practical robustness, making it genuinely suitable for real-world applications, where these unavoidable variations can otherwise completely cripple conventional analog circuits.
That's a very comprehensive case for robustness. Now, you mentioned low power regimes. We often hear about femtoampere currents, these unimaginably tiny trickles of electricity in highly specialized sensors or incredibly niche applications where every last drop of energy matters. But can SAC actually operate at these incredibly low power levels? Can it really push the boundaries of energy efficiency in AI?
Absolutely. And this is another fascinating aspect that truly highlights the versatility and potential of this framework, especially for next-generation AI at the extreme edge. The paper delves into what they call deep threshold operation, specifically to exploit the very lowest available current ranges of transistors, sometimes operating at currents orders of magnitude below what's typical even for low-power analog.
Deep threshold. How do they achieve that?
One ingenious technique they use is source voltage shifting. Imagine the gate of a transistor as a faucet controlling current flow. By slightly raising the voltage at the source terminal, they can allow the gate voltage, the faucet control, to go extremely low, effectively pushing the transistor into a deep subthreshold region.
So it's barely on.
Exactly. In this region, the transistor is just barely conducting, and the currents flowing are minuscule, almost approaching the level of leakage current as illustrated in Figure 5a. It's like turning the faucet to the absolute smallest drip possible, minimizing water usage.
Okay, source shifting. Any other tricks?
Yes, they also combine this with something called channel conduction manipulation. This involves connecting the body terminals of the transistors, another control point, to the highest potential, typically the positive supply voltage VDD. This further helps prevent unwanted channel inversion, current leakage paths, at these extremely low gate source voltages.
So two techniques working together to minimize current.
Right. Figure 5b shows how these techniques are incorporated into the circuit, and the results are quite impressive. Using these combined techniques, they managed to achieve operating currents down to an astonishing 1.97 femtoamperes FA for NOS transistors in a 180 nanometer CMOS process.
Femtoamperes, can you put that in perspective? That sounds ridiculously small.
It is. A femtoampere is a quadrillionth of an ampere, 10 to the minus 15 amps. It's an incredibly, almost unfathomably tiny current. For comparison, typical low-power analog might be in the nanoamp range, 10 to 9, or picoamp range, 10 to 12. This is orders of magnitude lower.
Wow. And the SAC function still works down there.
That's the key finding. Figure 5c clearly shows that even at these ultra-low, almost whisper-quiet current levels, the basic SAC circuit's characteristic HX shape is beautifully preserved.
That's incredible. What does that enable?
Well, what's truly revolutionary here is that this capability opens immense doors for extremely low power, always-on AI at the very edge of the network. Imagine tiny, self-sufficient smart devices, maybe in medical implants monitoring vitals or smart fabrics reacting to the environment, or remote environmental sensors that can perform complex AI inferencing for years on a single tiny coin cell battery.
Or even energy harvesting.
Or even by scavenging energy for their surroundings, light, vibration, heat gradients, without needing frequent recharges or battery replacements at all. This is truly a game changer for making AI ubiquitous and sustainable in ways that just weren't feasible before.
This raises an important question, though. So we've established that these SAC units are remarkably robust and scalable across different technologies, biases, and temperatures. They can even operate on fumes, practically. That's fantastic for the building blocks themselves. But the real acid test is, can they actually construct the complex mathematical functions needed for real-world machine learning tasks? I mean, the kind of sophisticated operations that power today's most advanced neural networks and AI systems, can you build real stuff with them?
That's the perfect question, and the answer presented in the paper is a resounding yes. The SAC units function effectively as fundamental analog standard cells, essentially, a versatile library of reliable, scalable building blocks, much like digital standard cell libraries.
Okay, a library of analog parts.
Exactly.
Yeah.
And the paper provides compelling demonstrations of how these can be used to synthesize a wide array of functions commonly found throughout ML architectures. Since the basic SAC prototype function HX can be mapped to an exponential function over a certain operating range.
Which is a very useful function in itself.
Extremely useful. It becomes a powerful, primitive building block that can then be used to construct much more complex functions. This includes crucial hyperbolic functions like cosine hyperbolic, cosh, and sine hyperbolic, sin, and other essential nonlinearities needed for neural networks.
Why are those nonlinearities so important?
Because neural networks, at their core, are cascades of linear operations, basically matrix multiplications and additions, followed by these nonlinear activation functions. Without the nonlinearity, the whole network would just collapse into a single linear function, severely limiting its power. Having these nonlinear activation functions readily available in a scalable, robust analog form is a monumental step forward for building powerful analog AI systems.
Got it. So the nonlinearity is key to the network's learning power. Let's zero in on some specific examples then. What are some of these key building blocks, these activation functions, that are truly the heart of modern neural networks, and how did SAC implement them?
Okay, the paper provides several compelling proofs of concept for these crucial ML functions, really demonstrating the versatility of the SAC approach. Expert speaker. First, the cosine hyperbolic cosh function. This is elegantly constructed by simply adding the responses of an SAC unit to an input x and to its negative x. Think of it mathematically as cosh x plus hx. Figure 6a in the paper shows the clever circuit implementation using these basic SAC blocks.
Okay, but just adding two outputs.
Pretty much. And what's truly important is that Figure 7a powerfully confirms its robust characteristic. It shows the function holds up across vastly different process nodes. Specifically, they show the older 180 millimeters and the advanced 7 millimeters, and impressively, across that wide range of operating temperatures we discussed earlier. It consistently performs as expected, regardless of the tech or temperature. Expert speaker. Next, the signed hyperbolic sin function. Similar idea to Kush, but this is achieved by subtracting the responses. Sin x equals hx. By strategically employing both N-type and P-type SAC cells in the circuit, as seen in Figure 6b, they again demonstrate its robust characteristics in Figure 7b. Again, reliable operation across those diverse process nodes and temperatures. Expert speaker. Then we have ReLU, the rectifying linear unit. This is absolutely a cornerstone activation function of modern neural networks. It's prized for its computational simplicity, it's basically max 0x, and its effectiveness in training deep networks. Yeah. ReLU is everywhere now. It really is. SAC implements ReLU using just 2 SAC units, as shown in Figure 6c. And again, Figure 7c clearly shows its characteristic response, which once again is impressively robust across process nodes and temperatures.
And what about variations? ReLU seems like it could be sensitive near zero.
That's a great point. They ran critical Monte Carlo simulations, which are essential for assessing reliability under real-world manufacturing variations. Figure 8a for 180 millimeters and Figure 8ben for 7 millimeters confirm extremely low output current deviation, a mere 3.11% standard deviation in 180 millimeters, for instance, indicating high reliability even with typical chip-to-chip variations around that crucial 0 point. Expert speaker. They also developed a compressive nonlinearity. This is interesting. They formulated a general function, phi(x), which can skillfully emulate both the classic tan hyperbolic tangent and sigmoid functions.
Which were very common in older networks, right?
Exactly, and still used in specific architectures like LSTMs or for outputs between 0 and 1. This general function is mapped to SAC computation as a combination of H functions involving constants, as seen in Figure 6ben. Figures 7ban and 7e clearly display the simulated tan-like and sigmoid-like responses, respectively.
And robust again.
You guessed it. Again, Monte Carlo plots for the sigmoid equivalent, Figure 8b, show excellent robustness with remarkably low deviation, for example, an impressive standard deviation of only 0.91% in 7 millimeter. This level of consistency in the face of variation is a huge win, especially for these smooth, saturation-prone functions. Expert speaker. Finally, Soft Plus. This is another important activation function that offers a smoother, differentiable alternative to ReLU. It looks a bit like ReLU, but curves gently near zero instead of having a sharp corner. It's implemented using 2 S3 SAC units. Remember, S is the number of splines, so this uses slightly more accurate SAC block, as shown in Figure 6c.
And the results?
Its robust response across process nodes and temperatures is evident in Figure 7. And once more, Monte Carlo results, Figure 8 and Figure 8, consistently confirm reliable performance, underscoring the intrinsic built-in robustness of the SAC approach for a whole suite of important activation functions.
Okay, so SAC can handle the complex, nonlinear activation part of machine learning with impressive robustness and scalability. That's traditionally been a huge hurdle for analog, so covering that is foundational. But what about other critical operations, like how do you handle weights?
You need multiplication.
Right.
And comparison or maybe even more complex decision-making processes that are absolutely essential for any functional neural network. Can SAC do those too? You're absolutely right to broaden the scope. Activations are necessary, but not sufficient. A neural network needs more. And yes, beyond just activations, the paper shows SAC can synthesize other complex machine learning modules that are fundamental to building full, high-performing neural networks. Expert speaker. Let's talk about winner-take-all, WTA and max circuits. A WTA circuit is designed to emulate the max function, which essentially identifies the largest input among several contenders.
Where would you use that?
It's crucial for things like competitive learning, find the most active neuron, or implementing selective attention mechanisms in more complex models. The SAC-based WTA, depicted in Figure 9, is elegantly modular, meaning it can be easily extended for any number of inputs, n inputs.
And does it work reliably?
Figures 10a through 10 clearly showcase its current and voltage characteristics for a simple 2-input WTA. They demonstrate incredibly consistent behavior across both 180 millimeter and 7 millimeter processes. Interestingly, when a specific design parameter, a tunable hyperparameter they call C, put to 0, the circuit behaves as a direct maximum input selector. It just picks the biggest input current. Expert speaker. This then extends naturally to the N of M encoder. This capability expands the WTA's functionality. Instead of just picking the single winner, it allows the circuit to identify the top M winners out of a larger set of N inputs.
Okay, like the top 3 out of 10.
Exactly. This is particularly crucial for building sophisticated, sparsely distributed memory systems or sparse coding schemes, where only a subset of neurons or information might be relevant at any given time. It sort of mirrors how biological brains often operate with sparse activity. Figures 10e and 10def clearly illustrate how the number of selected winners, M, dynamically changes as you adjust that hyperparameter C for a 5-input SACWTA, confirming its functionality and scalability in both 180 millimeters and 7 millimeter technologies. Expert speaker. They also implemented soft argmax. Now, argmax just tells you the index of the maximum value. Soft argmax is a smoothed, differentiable version of that, which outputs probabilities.
Why differentiable?
Because its differentiability allows for the crucial backpropagation and gradient-based training that neural networks rely on to learn. You need smooth functions for gradients to flow. The SACWTA can be specifically configured to implement soft argmax. Figures 10 gram and 10I demonstrate how different output currents activate based on that hyperparameter C, effectively representing the probability distribution and showing this precise capability across both process nodes. Expert speaker. And then, a truly major achievement, the 4-quadrant multiplier. Multiplication, specifically multiplying inputs by weights, is the most frequent operation in most neural networks.
Right, that W times X part.
Exactly. And traditional analog multipliers can be notoriously bulky, complex, and power-hungry. They've often been a bottleneck in analog ML systems. So if we connect this to the bigger picture, this is huge. The paper shows how scalar multiplication, XW, can be elegantly implemented using SAC cells through a clever series of additions and subtractions of the basic H function.
Using the same building block.
Yes. Using combinations of the basic hx function with different inputs related to x and w, equations 2430 illustrated conceptually in Figure 11. This fundamentally simplifies the multiplier compared to traditional approaches, making it much more compact and potentially much more energy efficient.
And does this SAC multiplier scale and stay robust?
That's the critical test, and yes. Figure 12a vividly demonstrates its scalability across process nodes, 180 millimeter versus 7 nanometer, and temperatures. And Figure 12b and 12c show robust characteristics across different operating regimes, WI, MI, SI, in both 7 nanometers and 180 nanometer, proving its reliability under diverse conditions. This means one of the most fundamental and repeated operations in a neural network can now potentially be done robustly, efficiently, and scalably in an analog fashion using SAC. That's a huge enabler for building powerful analog neural networks.
This sounds incredibly promising for building genuinely efficient ML hardware. We've got activations, we've got multiplication, comparison, the whole toolkit seems to be there. But let's get practical again. What are the real-world performance implications of SAC? Specifically, when we consider critical metrics like power consumption, the silicon area takes up on a chip, the cost, basically, and of course, the all-important accuracy. Are there any significant trade-offs we as designers or users of this technology should be really aware of?
That's precisely where the rubber meets the road, isn't it? Moving from capability to actual performance. And the paper provides a deep dive into these trade-offs, offering quantitative analysis that grounds these theoretical advantages in practical reality. Expert speaker. First, let's look at power and operation performance. Figure 13a shows something intuitive. As you'd expect, average power consumption increases with the number of parallel SAC units you use. More active parts generally mean more power. No free lunch there.
Makes sense.
But, more importantly, Table I summarizes critical operational performance parameters across the different biasing regimes. It reveals something really interesting. While computational efficiency, like operations per second per unit area, is highest in the strong inversion SI regime, that high-speed gear, we keep mentioning the best overall system efficiency, power efficiency, and lowest energy per operation, measured in picojoules per multiply accumulate, PJMX, can consistently be obtained in the weak inversion WRE regime.
So the slowest gear is actually the most energy efficient overall?
Yes, significantly so. This is a critical, perhaps counterintuitive finding for designing ultra-low power ML accelerators. It emphasizes that for highly energy-constrained applications, think battery-powered devices, edge sensors operating in that economy gear with SAC offers a significant advantage, even if it might mean a slightly slower computation overall. It's about choosing the right operating point for the specific application's needs. Maximum speed isn't always the goal. Sometimes minimum energy is. Expert speaker. Next, let's tackle mismatch and process variation again, but now looking at the impact on performance. In advanced submicron chip technologies, these tiny variations in threshold voltage and current factors are significant challenges for any analog circuit. They cause variability.
The unavoidable manufacturing randomness.
Exactly. But the paper demonstrates that for SAC circuits, the resulting output current variations due to factors like fin count in the 7-nanometer FinFET process, where the geometry of the tiny fins affects performance, or aspect ratio in the 180-nanometer planar CMOS, remain remarkably low. They stay within a tight 5% standard deviation margin, shown in Figure 13b, Figure 13c.
That's quite stable for analog.
It is, and it again underlines the inherent robustness of the SAC approach to those real-world manufacturing imperfections. It suggests that SAC designs will be far more predictable and reliable when they come off the fabrication line, compared to more sensitive analog designs. Expert speaker. Now for something quite ingenious related to noise, SNR analysis, signal-to-noise ratio. What's truly fascinating here, and a bit unique, is that SAC architectures offer a potential advantage in SNR compared to traditional analog systems, especially when used in parallel.
How does that work?
In typical analog systems, when you cascade stages, both the signal and the noise often get amplified, sometimes without a significant improvement in the clarity or quality of your signal relative to the noise. However, in parallel current mode SAC configurations, like when you sum the outputs of multiple SAC units, the correlated input signal amplitude increases linearly. For example, it doubles if you use 2 blocks in parallel.
Okay, signal adds up.
But the uncorrelated circuit noise, because it's random and statistically independent from block to block, only increases by the square root of the number of blocks. So for 2 blocks, the noise only increases by a factor of 2, or about 1.4.
So the signal increases faster than the noise.
Exactly. This means that for each additional SAC block connected in parallel, the overall circuit's signal-to-noise ratio effectively doubles, or increases by 3 dB, as detailed in equations 31-36. This is a powerful benefit for maintaining signal integrity and accuracy in larger, more complex analog systems. It allows them to remain precise, even when scaled up significantly by using parallelism. It's like adding more eyes to see a dim object. The signal, the object gets stronger, but the individual noise or fuzziness from each eye doesn't add up nearly as fast. Expert speaker. Let's consider area and power savings more concretely. We mentioned the number of splines, S, as a key trade-off knob. For instance, in an SAC multiplier, detailed in Table 2, increasing S naturally reduces error metrics, offering higher precision as expected.
More splines, better accuracy.
Right. But the most compelling data is the significant savings in resources this enables compared to conventional approaches. The paper reports that with an average absolute error of just 3.66% achieved using S3 splines, SAC offers up to 31.3% in area savings and up to 37.2% in power savings, compared to similar full-precision state-of-the-art analog multipliers.
Wow, over 30% savings in both area and power for similar accuracy? That's huge.
It's a massive win for practical chip design. Reducing area means you could fit more computing power on a chip or make the chip smaller and cheaper. And power savings directly translate to longer battery life, reduce heat dissipation, and enable deployment in more constrained environments. Expert speaker. Finally, pulling it all together on task energy efficiency. Table 3 further consolidates the energy efficiency findings across different functions and nodes. It clearly and consistently shows that the least energy consumption per operation is consistently observed in the weak inversion WI regime across both 180 millimeters and 7 millimeter process nodes.
So that ultra-low power WI mode really delivers on energy savings across the board.
It does. This powerfully reinforces the idea that SAC is particularly well suited for extremely power-constrained AI applications, making it potentially ideal for edge computing, wearables, and mobile devices where battery life is paramount.
Okay, so all these individual components, the scalable activation functions, the robust and efficient multipliers, the winner-take-all circuits, the impressive energy efficiency, especially in weak inversion, are incredibly compelling on their own. But the true test, the ultimate validation of this entire framework really, is integrating them into a complete system. How does an SAC-based neural network actually perform when put to the ultimate task of real-world AI classification? Does it hold up?
This is indeed the ultimate validation, isn't it? Moving from just smart building blocks to a fully functional, intelligent system that can perform a meaningful task. And the paper addresses this head-on. First, they detail the algorithm to hardware mapping. The paper meticulously outlines how a standard multi-layer perceptron, or MLP, a foundational type of feed-forward neural network, can be directly and elegantly mapped into the SAC framework. This includes the linear part, the WTX plus B decision function, where W are the learned weights, X are the inputs, and B is the bias term, and those crucial nonlinear activation functions we discussed, equations 3740.
How do they handle the bias term B?
Ah, cleverly. Those biases are implemented simply as constant currents injected or subtracted at the right nodes, leveraging Kirchhoff's current law. This means they don't require additional dedicated circuits just for the bias, which further contributes to the compactness and efficiency of the hardware mapping.
Nice. Simpler mapping means more efficient hardware.
Exactly. So for a concrete demonstration, they designed a three-layer neural network implementation, clearly shown in the block diagram in Figure 14, using these newly developed SAC standard cells for the neurons and multipliers.
And how is it trained?
This network was then trained using a specialized, variation-aware margin propagation algorithm. This training method is ingeniously designed to account for the expected hardware imperfections and statistical variations right from the very outset of the training process, making the final network more robust to the actual hardware it runs on.
Okay, so it's trained knowing it will run on slightly imperfect analog hardware.
Precisely. And the benchmark results on the ARMM and MNAS datasets are where SAC truly shines and provides compelling proof of its system-level viability. These results are summarized in Table 2. They rigorously tested the network's classification accuracy on standard datasets, activity recognition, ARAM, which involves recognizing human activities from sensor data, and the classic MNAS dataset of handwritten digits, a staple benchmark.
And the results. Did the analog network match software?
The crucial finding: the classification accuracy of the implemented SAC hardware nearly matches that of equivalent software simulations. This is huge. And this isn't just for one specific condition. It holds true across both 180mm and 7mm process nodes, and critically, across all operating regimes: weak inversion, moderate inversion, and strong inversion. For NMNS, they achieved a very respectable 93% accuracy on a scaled version of the network suitable for the hardware implementation.
Okay, 93% on MNIST is solid, especially if it holds across different hardware generations and operating modes.
It really is. This result is incredibly powerful because it unequivocally demonstrates the process technology, scalability, and bias scalability of SAC for building fully functional neural networks. It's a monumental achievement, showing that this analog approach doesn't inherently sacrifice the accuracy that digital has historically provided while offering those potential power and density benefits.
And you mentioned robustness in action. How did they test that at the network level?
Yes. Even more compelling is the demonstration of robustness in action. When they analyzed the network running the MNIST test set, they found that in practice, approximately 8% of the transistors in their designed SAC system actually shifted their operation from their intended biasing regime. For example, a transistor designed to operate optimally in weak inversion might have inadvertently moved into moderate inversion during operation due to real-world factors like input signal variations or local temperature changes.
So the hardware wasn't perfectly behaving as designed, which is realistic.
Exactly, it's real-world conditions. However, despite this measurable real-world deviation from ideal conditions, there was no significant drop in classification accuracy. The network kept performing well.
Wow. So the system just absorbed that variation.
It did. This brilliantly highlights the inherent bias scalability of SAC circuits at the system level. They gracefully handle these operational variations that are commonplace in analog hardware, rather than being crippled by them, which is a testament to the robust design methodology enabled by SAC and the variation-aware training.
That's really impressive resilience. How does it compare to other analog AI chips?
Finally, they provide a comparison with state-of-the-art analog artificial neural network, ANN implementations, summarized in Table V. This helps place SAC in the context of other research efforts. The SAC network achieves competitive energy per pixel, a common metric for image tasks like NIST, compared to other published analog ANN implementations.
Competitive, okay. Any standout results?
Yes, notably in the weak inversion regime, that economy gear we discussed, the SAC ANN implemented in the older 180mm technology consumed an astonishing 3 times less energy per pixel than a comparable system they referenced.
3 times less energy. That's significant.
It really is. Now, it's fair to note it did consume more power in the strong inversion mode compared to some others optimized for speed, but this data clearly shows SAC's significant advantage for ultra-low power applications. It gives designers the crucial flexibility to choose the optimal operating point WI for maximum efficiency, SI for maximum speed, tailoring the chip to their specific energy budget and performance requirements. This means you can truly design for maximum efficiency where it counts the most.
Wow. This has been a truly deep dive into some potentially game-changing technology. We've seen how shape-based analog computing, or SAC, fundamentally tackles these long-standing, seemingly intractable challenges of scalability and robustness that have historically held back analog computing from truly excelling in machine learning.
Yeah, it really feels like a breakthrough.
It's an elegant physics-based solution to a very, very difficult problem that many thought might be unsolvable for general-purpose analog computation.
Indeed. By ingeniously generalizing that margin propagation framework and introducing this flexible multi-spline approach, SAC enables analog circuits to be designed as robust, predictable, standard cells. That's the key takeaway for me.
Analog standard cells.
Exactly. Cells that are remarkably immune to variations in transistor biasing, different manufacturing process nodes, and even wide temperature fluctuations. This unprecedented ability to directly trade off computational accuracy with power consumption and silicon area, much like in digital design, is a crucial leap towards the widespread adoption of analog AI.
It sort of democratizes analog design, maybe?
I think so. It moves it from a bespoke craft, requiring deep, specialized knowledge for each node, towards a much more scalable engineering discipline, potentially enabling faster design cycles and broader use.
So what does this all mean for you, our listener? Imagine a world where the AI in your smart devices, everything from tiny wearables and environmental sensors, perhaps even embedded in things like smart fabrics or vital medical implants, runs with unprecedented energy efficiency and computational density.
Really pushing intelligence out to the very edge.
And critically, it does this without sacrificing the accuracy you'd expect from today's powerful digital systems. This research is laying the foundational groundwork for that future, a future where sophisticated analog intelligence can thrive even in the smallest, most power-constrained devices.
It could dramatically extend their battery life, maybe allowing them to run for years, or significantly expand their capabilities within the same power budget. We're only just beginning to imagine the possibilities.
Yeah, the ability to synthesize this comprehensive library of complex ML functions, from fundamental activation functions to sophisticated multipliers and even entire neural networks, all in a scalable and robust analog fashion, truly opens up vast new horizons.
Absolutely. The consistent performance on benchmarks like MNIST, with classification accuracies nearly matching software simulations and demonstrating those incredible energy savings, especially in weak inversion, points to a very exciting path forward, perhaps toward the automated design and synthesis of large-scale analog processors in the future.
Yeah, automated analog design. That's the dream.
We are truly moving towards an era, I think, where designers can leverage the absolute best of both worlds, analog's intrinsic efficiency and digital scalability and design methodology, potentially in a unified, incredibly efficient manner. Maybe even hybrid chips that use SAC for the heavy lifting.
It feels like a foundational shift, maybe a new chapter in computing, or at least in how we build AI hardware. So, my provocative thought for you today is this. Imagine a world where your smart devices run AI tasks with incredible speed and minimal power, all thanks to circuits that understand the nuances of shapes and continuous signals, rather than just the stark binary world of zeros and ones. How might this fundamental shift in computing fundamentally change the design and capabilities of our everyday technology? What completely new, previously unimaginable AI applications might become possible when power is no longer the primary bottleneck, when intelligence can be truly ubiquitous, always on, and whisper efficient literally everywhere?